Okay, the next thing we're going to talk about is partial fraction decompositions, which you probably saw in pre-calculus, but maybe not, and you may have forgotten anyway. So this is going to be something we're going to need to do in order to integrate lots of the integrals that have rational functions in them. We want to break the rational expression, like 5x minus 3 over x squared minus 2x minus 3, something like that, up into a sum of two simpler fractions. This is called the method of partial fractions or partial fraction decomposition. So the question is, how do you get from here to here? And that's what we're going to talk about right now. So it depends on the factors of the denominator, how you're going to set up the problem. The first type of denominator that we're going to look at is non-repeated linear factors. So in other words, we have x with no exponent on it. And that's only though after we have factored. When that's the case, that you can factor the denominator into all linear factors, none of which are the same, then you know that you're going to be able to set up a sum where each fraction in the sum has one of those factors as its denominator. And in the numerator is some unknown constant value. Those are called undetermined coefficients, the A, B, and C there. So right now, we're just going to practice setting it up. We're not actually going to we're not going to solve for A, B, and C. We're going to worry about that in a minute, how you do that. But for right now, I just want you to get used to how to set it up. So for example, in example 1, expand the quotients into partial fractions. Do not find the undetermined coefficients. So we're just going to leave it A, B, and C. All right, the first step is to factor the denominator. So this is equal to, how would I factor 2x squared minus 8x? It has a 2x in common, leaving behind x minus 4. Okay, so would you agree that both of those factors are linear? Yeah. And they're different from each other. They're unique. So that means that we can break this apart into a sum of two fractions. One that has the 2x as a denominator, one that has an x minus 4. We don't know what these coefficients are going to be. We're just going to say a over 2x plus b over x minus 4. Again, and we'll talk about how to find the a and the b, but at least we know that it can be written in that form. All right, why don't you try part B there? Okay, does the denominator in part B factor? Okay, what does it factor into? Good, x minus 4, x minus 3. Okay, so that means since they're both linear and they're distinct, we have a over x minus 4 plus b over x minus 3. That would be the form that we know. We can find an a and a b to make that happen. All right. And by the way, it doesn't matter how many linear factors. I could have 16 of them, then I would have to add up 16 fractions. All right, so now let's go ahead and do another survey here. Which one of these would be the correct form for the partial fraction expansion of x plus 4 over x squared minus 4x? And let me get the poll going. Does the denominator factor? Yep, just factor out an x, leaving an x minus 4. So we need a factor of x, so we need a factor of x minus 4. Those are each our denominators. Now, if there are repeated linear factors, in other words, if you factor the denominator and you find there's a linear factor raised to a power, that would be another way of saying that, then you have to have a denominator for each power of that factor from 1 up to whatever the power was. So for example, for this guy here, we have a linear factor x, we have a linear factor 3x minus 1, but then we have 2 factors of 2x plus 5. So you have to have a 2x plus 5, but then you also have to have, which is a power of 1, by the way, and then you also have a 2x plus 5 squared. Now, if this had been a 3 on this power, this exponent of p of x, then we would have had to have even yet another one with a power of 3. You have to go all the way up to whatever the power was. You need 1 for each. That makes sense? Let's try another example. So it says expand the quotients into partial fractions. Do not find the undetermined coefficient. So we have x over x squared minus 2x plus 1. All right, how does this factor? Yep, x minus 1 squared. Okay, so we're going to need one denominator that just has x minus 1 and one denominator that has x minus 1 squared. Call one undetermined coefficient A, the other one B, and you're done. How does part B's denominator factor? Yes, except I'm going to break this x squared minus 1 up as well. So we have x minus 1 squared. How does x squared minus 1 factor? Doesn't it factor in x minus 1, x plus 1? But we have that cubed. So this is going to be x minus 1 squared times x minus 1 cubed times x plus 1 cubed. So actually, how many copies of x minus 1 do we have? More than that. We have 5 of them. So this is really x minus 1 to the 5th times x plus 1 cubed. Okay, so we know that I'm going to write it below because it's going to get long. Oops. Okay, so we have 3x plus 5 over x minus 1 to the 5th x plus 1 cubed. 2 linear factors, but with multiple copies. Let's start with the x minus 1. So we're going to have an x minus 1, x minus 1 squared, x minus 1 cubed, x minus 1 to the 4th, and an x minus 1 to the 5th. Okay, but we're not done because now we need the x plus 1. So there would be an x plus 1, there would be an x plus 1 squared, and an x plus 1 cubed. Get the idea? All right, so which one of these would be the correct version of our correct partial fraction expansion of x plus 4 over x squared minus 4x squared? Let me pop up this thing. Let me get the poll going here. Okay, I started the poll. Oops, I covered the problem. Sorry. Okay, 30 more seconds. Last chance. Okay, I'm gonna stop the poll. All right, you did great. 78% of you picked C, which was the correct answer. So let's see why. So in the denominator here, inside the parentheses, we have x times x minus 4, but that whole thing is squared. So that's the same as x squared times x minus 4 squared. So x squared is not considered a quadratic. It's considered multiple copies of one linear. Okay, so you have to keep that in mind. So, as we haven't even seen what to do with a quadratic yet. So we're going to need one of each power up to 2 for the x and one of each power up to 2 for the x minus 4. And that's why C is the correct answer. Any questions about that one? Okay, now quadratic factors. Now these have to be irreducible. What does irreducible mean? Cannot be factored, at least not across the real number system. Everything can be factored. If you use imaginary numbers, everything can be factored down to linear factors. But if you don't, then there are irreducible polynomials that cannot be factored down. So if it contains a quadratic, two unique quadratics like here, it's going to be one denominator of each, but in the numerator, we are not going to have a constant in A and a B. We're going to have a linear expression, AX plus B or CX plus D. And then the same thing goes if it's repeated, you have to have one of each power. So if you have AX squared plus BX plus C cubed, then you have to have ax squared plus bx plus c denominator, ax squared plus bx plus c squared denominator, and ax squared plus bx plus c cubed denominator, like that. Okay, so for example, here we have the here we have 2x plus 5 over x squared times x minus 1 times x squared plus 4. So the factor of x squared, remember, that's a linear x, but with 2 copies of it. So we're going to have an x and an x squared for that one. For the linear x minus 1, we just have one denominator. For the x squared plus 4, is that irreducible? X squared plus 4 can be factored? No, it cannot be factored. So yes, it is irreducible. So that means that it's just going to be one denominator, but instead of a constant on top, it's got a linear combination. It's got dx plus e on top. Okay. All right, so let's take a look at example 3 here. It says expand the quotients into partial fractions. Do not find the undetermined coefficient. So we have x squared plus x over x to the 4th minus 3x squared minus 4. By the way, one thing I forgot to mention is all the problems we've looked at so far, they are proper fractions, not improper fractions. How do you know the difference with polynomials? It's the degree of the x. So every one of these, the x on top has had a lower highest degree than the ones on the bottom. All right, anyway, how can we factor x to the 4th minus 3x squared minus 4? Close. Yes, very good. So it fits the pattern of x squared minus 3x minus 4, right? It's quadratic in form, even though it's not quadratic, and it factors similarly. So it's going to be x squared minus 4 times x squared plus 1. Can either of those factor further? Yeah, the difference of squares can, but the sum of squares cannot. That would give us a complex root. Oops, I just wrote the wrong number. Yeah. X minus 2 times x plus 2. And there's nothing we can do with the x squared plus 1. All right, so this is x squared plus x over x minus 2, x plus 2, x squared plus 1. So we have 2 linear distinct factors and then a distinct quadratic factor. So we're going to need just one denominator of x minus 2, one of x plus 2, and one of x squared plus 1. And what's going to go on top of the x minus 2? A. What's going to go on top of the x plus 2? And on top of x squared plus 1, cx plus d. Okay,